Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to introduce the idea of kinetics. Now, before we do that, I just want to take one step back and talk about the difference between thermodynamics and kinetics. In our previous units, we were talking about thermodynamics. Specifically, we were talking about delta G, which is Gibbs free energy. And if delta G is a negative sign, that means a chemical reaction will take place. If it's positive, it won't take place. So the big idea in thermodynamics is, does the chemical reaction take place or not? Okay. Kinetics is, if the chemical reaction does take place, how fast is it taking place? Like, how fast is it reacting? So whenever you see anything about kinetics, we're talking about, how fast is the chemical reaction taking place? And that's going to be our major idea today. It's like we're going to be talking about rates and how fast the chemical reactions are actually taking place. Okay. So now that I said that 5 million times, let's jump into some factors that affect how fast a chemical reaction will take place. And in your reading, you're going to find out there are kind of like four major factors. The first one, and this is the one that we're going to talk about the most, is going to be concentration. The concentration of the chemical reaction, or of the reactants, will determine how fast a chemical reaction will actually take place. Temperature is another big cause. Most of the time, as we increase the temperature, the chemical reaction is going to move faster. A catalyst, if it's introduced, which is a chemical that is not a reactant, but it is present at the beginning and the end of the chemical reaction. And some catalysts can actually speed up chemical reactions. And of course, if we have an increased surface area, there's more places where the chemical reaction can take place. Increasing the surface area will also increase the kinetics of the chemical reaction, or how fast it takes place. So these are the major factors: concentration, temperature, catalyst, and surface tension. So like I said, when we're talking about kinetics, we're always talking about how fast. So I got a couple examples up here. I got a chemical reaction of A going into B, versus a chemical reaction where A is changing into 2B, and we're going to talk about the rates of both A and B. Now, when we get into rates, I want to do a little bit of review, maybe from like an earlier science class. Like if we're trying to figure out the rate of how fast a person's moving in the classroom, I want to let you guys know the calculation that we would use for how fast, or the rate of the chemical reaction, or how fast the person is moving, is always going to be the change in distance over the change in time. That's how fast we can figure out how fast somebody's moving in the classroom. We take a position change, we see how much distance they've traveled over a certain amount of time, and if you take the change in distance over the change in time, you will get to know how fast that person's moving. Well, chemical reactions are no different. However, instead of the change in distance, we're going to do the change in molarity. And a lot of times when we talk about molarity, we put it in a bracket. So when this B and A are in brackets, that means we're talking about concentration, or molarity. But it's going to be the change in molarity over the change in time instead of the change in distance over the change in time. Both of them are going to give us some type of rate. Well, I have some incomplete data table here. Before I can calculate rate, I need to figure out, well, what is the molarity of B after 10 seconds and after 20 seconds, And this is the way we kind of go about doing those things, So what we're going to do is we're going to try to figure out, well, how much A is reacting? Well, if it starts out at 1 and it goes down to 0.5, that means 0.5 moles or molarity of A is reacting. So if I take those 0.5 moles of A, and that's going to be moles per liter, because we're talking about molarity here. And if I go from moles of A to moles of B, it's a 1-to-1 relationship. However, the moles of A are going to cancel out. 0.5 times 1 divided by 1 is going to be 0.5. So 0.5 times 1 divided by 1 is going to be 0.5. If we do that over here, if we take that same 0.5 moles per liter of A reacting, and we go from moles of A to moles of B, but now it's a 1 to 2 relationship, okay? Well, 0.5 times 2 is going to be 1.0 as far as the molarity, because for each A that reacts, you're actually producing 2 Bs, okay? So this is going to increase, okay? And we do the same thing for the next part, okay? After 20 seconds, it looks like 0.75 has reacted. Well, 0.75 times 1 divided by 1 is going to be 0.75. Okay. Same thing here. From 1 to 0.25 is going to be 0.75. Okay. And 0.75 times 2 is going to give us 1.5. Okay. So we're just using some stoichiometry here to figure out what these values will be. Okay. As this reacts, it's going to be 1 to 1. As this reacts, it's going to be 2 to 1. So our numbers over here are going to be larger. Okay. Now that we have that figured out, we can figure out the change, okay, in concentrations, okay, and that will give us a rate. So we're basically going to be using this equation to figure out the rate, okay. So let's talk about the rate change in the first 10 seconds, okay. So we want the rate in the first 10 seconds, okay. So we're going to do the change in molarity over the change in time, okay. So in the first 10 seconds. So we're going to start out with A, okay. So remember, whenever we do the change in anything, it's always final minus initial. So it's going to be 0.5 minus 1.0 over 10 minus 0, okay. So what I did is I did the change in A over the change in time, okay? And this is going to come out to 0.5. It's negative 0.5, and this is going to be 10. So this is the units that we're going to get, because this is going to be molarity, and this is going to be seconds. So the rate is going to be in molarity per second, okay, for the first 10 seconds, okay? Let's talk about the second 10 seconds, because I want you to see something that's taken place here that's kind of really important when we're talking about kinetics, okay? If we're going to do the second 10 seconds, okay, and we do the change in molarity over the change in time, okay, well, the second 10 seconds is right here, so 0.25 minus 0.5, so 0.25 minus 0.5 over 20 minus 10 is going to give us negative 0.25 over 10 seconds, which is a negative 0.025 molarity per second. So my question to you is this, okay? What's happening to the rate, okay, as the chemical reaction takes place, okay? Well, it looks at the first 10 seconds to be much faster than the second 10 seconds. And that's how a lot of our chemical reactions are going to work with kinetics. They're going to start out really fast, and then they're going to slow down. So if I was clapping my hands like as the chemical reaction's taking place, it would sound something like this. It'd be like fast in the beginning, and then gradually slow down, okay? And that's how these chemical reactions take place, because one of the factors that affect how fast a chemical reaction can take place is the molarity. And as you can see, as time goes by, the molarity is decreasing. And if the molarity is decreasing, then the rate of the chemical reaction is going to decrease as well, okay? Now, if we did the same thing, okay, if we're talking about the rate of A here and we compared it with the rate of B, you're going to get kind of the same number. So let's kind of like check this out, okay? If we do final minus initial, it's going to be 0.5 minus 0, and we're talking about B now, okay? So initially we were talking about A, but 0.5 minus 0 is going to give us 0.5, but it's going to be positive, okay? So that's going to end up being positive. And then down here, 0.75 minus 0.5 is going to give us a positive 0.25. But as you can see, the rates are going to be the same for A and B, and that's only because it's a 1-to-1 ratio, okay? If it's not a 1-to-1 ratio, the rates will not be the same, and we can see that a lot in our second example, okay? So let's kind of do the same thing that we did over here. Let's start out with talking about the rate of A in the first 10 seconds, okay? So it's going to be 0.5 minus 1. Okay, so 0.5 minus 1 is going to give us, try my 0.5 a little bit better. So 0.5 minus 1 is going to give me negative 0.5, and that's all over 10 minus 0. So this is going to be a negative 0.05 molarity per second, just like the last one was, because we're dealing with the same numbers, okay? And then if I do the second 10 seconds, it's going to be 0.25 minus 0.5 over 20 minus 0, or 20 minus 10. So this is going to be a negative 0.25 over 10, which is going to give us a negative 0.025 molarity per second. Okay, so once again, as the concentration goes down, okay, the rate of the chemical reaction is going to go down. So it starts out really fast and then slows down. Okay, well, what about the rate of B? Okay, let's talk about the rate of B. If we're going for the first 10 seconds, so we're going to go here for B, 1 minus 0 over 10 minus 0. So that top number is 1, this bottom number is 10. This is going to be a positive 0.10 molarity per second for B. Look at these rates, okay? This one is twice as fast as this one, okay? And let's do it for the next piece, okay? The second 20 seconds. 1.5 minus 1 over 20 minus 10, okay? That's going to be a 0.5, and this is going to be a 10. So that comes out to positive 0.05 molarity per second for B. And this is twice as fast as this one, okay? So no matter where we're at, okay, the rate of B is going to be 2 times as fast as the rate of A. And that's because of the coefficients, okay? So if the coefficients are different, okay, the rates are going to be different, okay? If the coefficients are the same, the rates will be the same, okay? And the analogy that I like to use is, like, think about building cars, okay? If I was building a car, I'd need 1 frame and 4 wheels to kind of make a car. I hope you understand that the rate of the wheels is going to be 4 times as fast as the rate of the frames when we build these cars. And that's because for every frame that comes by, they have to put 4 wheels on it, okay? So we better have a big pile of wheels because we're going to go through a lot of wheels versus the amount of frames that we're going to go through because of the coefficients in the balanced chemical equation. Okay, so hopefully that analogy makes sense. Okay, so when we're talking about these rates, okay, the last thing I want to kind of leave you with this introduction is that it's an average rate. And the analogy that I use for this is I like to talk about Usain Bolt, okay, which is the fastest person alive to date, okay, and this is like 2024 in the 100-meter dash, that is, okay. So if we're trying to figure out Usain Bolt's rate, we would take the change in distance over the change in time, and he runs 100 meters, okay, in 9.58 seconds, okay. And if you divide these two numbers, you're going to find out that that's 10.4 meters per second, which is very, very fast, okay. Now, what I want to say, when we do this change in distance or change in molarity over the change in time, like we've been doing on the board, this is actually an average rate, okay? Because when the gun goes off in the race and Usain Bolt takes that first step, okay, that first step, he's not moving 10.4 meters per second. In fact, it takes him probably 30 or 40 meters to get to his top speed, and his top speed is going to be greater than 10.4 meters per second. All we know is because we have the change in distance over the change in time, we know over that 100 meters, he's averaging 10.4 meters per second. So if we have these points, in the first 10 seconds and the second 20 seconds, that's going to be an average rate, okay, for the chemical reaction in those first 10 seconds or in the second 10 seconds of the chemical reaction. That's all we know because we have these moments in time where we've calculated the molarities at these different times. So everything that we're doing on the board up here is what we call an average